Well, good morning, everybody. It's a real pleasure to be here and to see friends and colleagues that I've worked with in this issue for 10 years and more. I'm representing Engineers Canada as the profession of engineering. Engineers are a major user of climate data and information, and our national body of Engineers Canada has been actively involved in climate change adaptation for more than 10 years. In fact, we've been working on it since 2001. Just by way of introduction, we are the national body for the profession of engineering, the second largest profession in Canada. Our members are the professional engineering associations at the provincial and territorial level, so Professional Engineers Ontario is a member. So we don't deal very much with the individual engineers, but more with the constituent associations. And we do a lot of coordinating functions, that sort of thing, on qualifications. We get involved from the education of engineering students right through to the practice. You can see some of the statistics up there. And we're also the national, international voice of the profession. So we've been actively involved in climate change for a long time. So I'm going to speak to you today from the perspective of climate data and information needs for infrastructure engineering. So that's one of the key areas that engineers are very involved with. And you know, infrastructure is a very broad and diverse set of facilities that provide services in our quality of life, from shelter, heat, light, and power. And there's a lot of different kinds of infrastructure, that each of which have their own needs for climate data and information. And all of these infrastructures interact with the climate and are affected by the climate. So we need to know what's, as engineers in the design, planning, and operation, what the climate is going to do both now and in the future. So we, as professional engineers, we have a code of ethics that tells us that we hold paramount the health, safety, and welfare of the public and regard for the environment. So we're here to serve the public, and public infrastructure is a key element that we need to be concerned about. And we have to think about it from the point of view of the economic, social, and environmental factors. And really what we're seeing with the changing climate is that, especially with our existing infrastructure, that some of our older infrastructure is at threats to climate. We've seen it already with a number of extreme events. And we want to make sure that, you know, as engineers, it's our responsibility to make sure that infrastructure is operated and maintained over its service life, which is often up to 100 years, depending on the kind of infrastructure. We look at the point of view of what are the risks of climate to infrastructure, and why do we need to look at this as engineers? Well, you know, as I mentioned before, we are there to serve the public. Public safety is a big concern, but we also want to, as engineers, we serve our clients and our employers, to particularly at operators of infrastructure. And they're concerned about, you know, making sure that they provide levels of service for the infrastructure. We want to make sure that there's the minimum of disruptions from climate events, such as the ice storm from Toronto last year, where people lost their power for up to 2 weeks, I gather. And obviously part of the whole service delivery is optimizing the service, so you want to manage that infrastructure over its life cycle, the operations and maintenance, the year-to-year activities that need to be taken to maintain the quality and operation of the infrastructure. Another thing, you want to avoid surprises. You know, when you get an extreme weather event, you know, all of a sudden you have a $50 million bill that you didn't have the day before because you've just had all the damage that came from that extreme event. So our goal is really, we want to reduce damage and costs, and that's part of our responsibility as engineers. So we are recommending, as a best practice in engineering, that we must actually assess the risks of climate to infrastructure as a first step in adapting infrastructure and changing climate. The application of climate data from the point of view of infrastructure engineering is these four areas, general areas. I just mentioned engineering vulnerability and risk assessment as the first step. Taking that information, using it for planning and design of the infrastructure, also applying it to operations and maintenance, and then ultimately you want to reflect the climate experiences you have in codes and standards, which is our basic tools to use for design and also for the management and governance of infrastructure. risks of climate are highly, there's a lot of the extreme events here, and this is a table put together by Environment Canada a few years ago that just sort of gives an overall view. There's a lot of red in this picture, and engineers don't like red, which in this case means failure. So you can see that a lot of these, there's a number of climate parameters. This is by no means the entire list, but you start to see how we want to get into some of the details around climate information for different kinds of infrastructures. And you can see that there's a variation in impact amongst the structures. So you have to kind of look at what kind of infrastructure you're designing and operating to determine what the climate information needs are. And you know, one of the things that you see in the future climate is, of course, these are the IDF curves, and you're seeing shifts as we go forward in the projections that, you know, certain events are going to happen more frequently and more intensely. And IDF curves and future IDF curves are a very important tool in engineering design, operations, and management. We do have certainly consideration of climate today in our codes and standards, particularly our National Building Code. Is included for safe and economical infrastructure. The 2015 Building Code just been published. Takes into account and specifies particular climate parameters. You can see a number of these. This is really getting into some of the details that we need to get into as engineers. And for the first time, there's actually mention in the Building Code about climate change risks. Now, it's only an introductory kind of thing, and the next cycle of updating on the Building Code is 2020, and they're already starting to plan for that. And so I think over the next 2 to 3 years, we need to really give a solid input into the National Building Code process so that we can make sure that we can account for future climate. And climate data and information is very important input into that discussion. So our concern is that the climate is not going to necessarily represent the future. We based our designs on past extremes. And engineers are typically very conservative people because we're responsible, we're legally responsible for the safe infrastructure. So we've often used, you know, past performance as an indicator for the future. But now with this variable called changing climate, we're seeing changes in the extreme, and we're seeing thresholds of infrastructure components being exceeded where you get failure. And so therefore, we need to come up with a new strategy, and this is almost a paradigm shift for engineers to come up with a new strategy in light of the changing climate. So that relates to the climate change information that's used in the planning and design process. So I'm going to give you Engineering 101 for those non-engineers here, just to categorize how small changes in climate can lead to a catastrophic failure. So you start off with an infrastructure with a design capacity. You have a design load, so obviously the capacity has to exceed the load to be a safe structure. You add, as people may know, the safety factor on to account for some of the uncertainties in the behavior of the infrastructure. Over time, as that infrastructure ages and is getting used, there is a reduction in capacity. You also see this, the impact with climate is not a precise science, so there's also a reduction in capacity, but still exceeding the load. And on the design load side, you see a change of use in infrastructure over time, and an example of that is bridges, where often bridges capacity is exceeded by up to 50% of its original design, and the bridge still is safe and it works, but it also increases the loading on that bridge. Now, if you have a severe climate event at a particular point, you see load exceeds capacity, and bingo, potential failure condition. There's the red again. We don't like red. So this is the kind of thing that we're concerned about. This is why even small changes in climate can lead to that, and that's that threshold idea. And so we actually can base this on actual data and information. This is a study that was done in Australia, where they found a 25% increase in peak, resulted in a 650% increase in building damage. So you can see that all of a sudden, when it gets over a certain wind speed, you're seeing failure and damage on the infrastructure. So they concluded the small increases can have large increases in damages. So there's actually data in Ontario that's produced that's very similar to this. It's not published yet, but the hope is that in the coming months we will actually have this kind of information. Another idea is on the ice storm. You may recall the ice storm from 1998, and of course, from last year. And you can see this whole notion of thresholds again, where on transmission lines, where when you get certain amounts of extreme freezing rain accumulations, you start seeing cascading failures here. So, for example, at 12 to 20 millimeters, we're seeing line outages on power transmissions because the trees are breaking and they fall over onto the lines and disrupt power. And the more ice that accumulates, the more the severe the impact is, and obviously the cost as well, and the length of disruption. So what engineers are really interested in is extremes, and because that's what we have to design for. We can't, what means are, they're kind of like okay, but they're not really what we need for design purposes. So when you see the climate is changing, and what you see here is we're really looking at what is the maximum kind of number, one might say, for a particular climate parameter, and also what is the probability of that number occurring, okay? So you have certain thresholds there where if they're exceeded, that could result in damage or failure. So if you see a shift in the climate, that means that the probability of that happening is increased. So this is the kind of thing that we're trying to look at, is not only what is the climate parameter, but what's the chances or the probability of that happening, which is an element of the risk to infrastructure. We have used this analogy to come up with a protocol. I'm only not going to talk about it very much today, other than to say we have this protocol, a risk screening tool, which analyzes the interaction of climate elements with infrastructure. We've done over 40 projects, all completed and underway with this protocol across Canada, quite a number in Ontario, and some of the folks here have worked with us in the past on this. This is the tool that we've been using as engineers to understand vulnerabilities and risks to infrastructure. And and of course this has actually helped us to evolve our needs and understanding of climate data and information for the profession. And just some of the lessons we've learned from these 40 plus, and it's for a wide variety of infrastructures that we've looked at, but just to give you some sense of, what are the priorities in terms of from engineers' perspective. Of course, precipitation is a very important one. Of course, we've all been impacted one way or another, and it's not just, sort of the average annual rainfall. It's the high intensity, short duration rainfall that causes these kinds of situations that you see in the picture there. And these, a lot of times, one of the big vulnerabilities we found in all these studies is the interruption in power supply. So all the climate information that supports the reliability of power in Ontario and other places, that's extremely important because power drives infrastructure, most infrastructures. If you lose that power supply, it can even hurt the backup power supply, and you get a public safety issue. Also, combinations of events can have more impact than discrete ones. Often the data is very dated. We did a study in Welland where they actually had to use an IDF curve from Buffalo because they didn't have an IDF curve from Welland. So that's pretty sad. Obviously we want to look at regional climate expertise. So you want to get site specific because that's our goal as engineers. Is we're not looking at sort of the big picture. We're looking at specific infrastructures. We need regional climate expertise, and we need to have climate experts working with engineers and other professionals to understand the vulnerabilities and risks. And it's really key, I think. Engineers will never be climate scientists. We need climate scientists to work hand in hand with engineers to understand that climate data information. And I would challenge anyone who isn't a climate scientist to try to become an expert, because it's really tough, as Ryan was explaining there a little bit. Obviously using ensembles, Ryan mentioned about the large ensembles versus the small. I think a driver there is cost and complexity. The more models that you bring in, the costlier it is, and as engineers, we don't really need precision, we need accuracy. Obviously you need to understand the current climate, because then you can understand to project in the future. And obviously monitoring and maintaining, we need to maintain at least our existing climate network, and and then if we can, expand it to start to For example, put a weather station at the infrastructure that you're at and start collecting data, so when you want to rehabilitate that 20 years from now, you've got a 20 years data set to work with. So I'm going to give you 3 slides here that get really into some of the details of what we as engineers want. And we would be happy to engage in more detailed discussions, which we can't do today. We'll try and do some of that around the table. But we've got a number of climate parameters. I'm not going to go through all of those, but these are some of the higher priorities. And these are by no means all of the climate parameters. But these are certainly the ones that we need. And some of that information is not available, or as particularly in climate projections. We got to understand our new thresholds for damage and failure in operations and maintenance. So we want to know, like, if an extreme event's going to happen during the lifetime, but also, this year, is something going to happen that we maybe want to plan for in our operations and maintenance? We want to update the climate parameters in the Ontario Design Codes and Standards. Other aspects are extreme values and probabilities uncertainties, because we need that for our design. We need mean values for planning and executing operations and maintenance. So we're not saying that we don't need them, but it's for different purposes. We need to know ranges of uncertainty, because that's something that we can then use our judgment on. It has to be scientifically defensible. The climate scientist has to tell us this data is scientifically defensible. It may not be to the 4th decimal place, like the next point says, accuracy, not precision. We don't really need the 4th decimal place. We just need, a range of numbers that we can use that has some certain levels of confidence around it. And regional and site-specific, that goes without saying. Then, of course, in terms of up-to-date current climate data and information, the 30-year normals and extremes, we want to press on Environment Canada to make sure that most recent 30-year data set is available, updated IDF curves. We would like provincially endorsed databases and climate projections, not just this ad hoc collection, but let's have the province actually endorse a set of climate data that we all can use, so we're all speaking from the same songbook. And of course, online user-friendly interface, training and education is another aspect. So just a couple more slides. These are strategies to improve infrastructure, climate, and weather resilience. We have risks from climate now. It's not just in the future, but even now. If you see all the extreme events we've had, in Toronto and Calgary and those places, we've got to understand what our risks are now. So that's involving current climate. And of course, there's a number of strategies. There's also the climate change in the future. And I'm not going to go through all of these, but just to say that climate data information has a role in many of these kinds of solutions. And just to give you a sense of how this starts to translate, in the engineering profession, here's a guide that's been prepared by the BC Ministry of Transportation and Infrastructure on best practices for climate data information, recently published about 6 months ago. This is just the climate aspect. I'm not going to go through this in any detail, but just to say that we're actually getting it now into things like best practices. We've also published a model guide on climate change adaptation principles for engineers, which we hope to make public within the next 3 months. So we're getting our act together with respect to responding to climate change and adaptation. Another element, of course, in the longer term is new and updated codes and standards, and there is work going on there. I mentioned about the building code, but there's also some CSA standards from the north that are, but you need evidence, and that's the thing with codes and standards. We need to get evidence. So that's a very important element also in climate data and information. So my concluding remarks, last 2 slides, is that building new infrastructure and rehabilitating existing infrastructure, because we got a dual problem here, is new infrastructure going forward, but we also have a lot of existing infrastructure that's aging rapidly. We have to consider the current and future climate risks, and if you don't do that, and you're going to be incorporating vulnerabilities that will cause service disruptions, damage, and failure, these will negatively impact public health and safety, our quality of life, and increase costs to the government, private sector, and society. And finally, my message to the climate community is scientifically defensible current and future climate data and information is vital to enable engineers to cost-effectively design, operate, and maintain climate-resilient infrastructure over its service life. Thank you.